we are going to look at the energy stored on a capacitor, and from that result we're going to look at a parallel plate capacitor and determine the energy density in an electric field. Let's look at the following circuit. We have a DC power supply that is in series with the resistor and a capacitor, and a switch that we're going to close at t equals 0. Let's start with the capacitor uncharged. So Q at t equals 0 is going to be 0. When we close this switch at t equals 0, a current is going to start to flow, and that current is going to charge the capacitor. The voltage across the capacitor will be the charge on the capacitor divided by the value of the capacitance. So the voltage across the capacitor will start at 0 and build up to the value of our DC power supply. And so the final charge on the capacitor divided by the value of the capacitor will be that value of our DC power supply. While current is flowing, the power supply will be delivering power. Some of that power will go into heating the resistor, and the rest of that power will be stored on the capacitor. The power being delivered by the DC source will be the product of the voltage of the DC source times the current that is flowing. So work is done in charging up a capacitor, and summing up all that work to go from a value of charge of 0 to a value of Q will tell us how much energy is stored on our capacitor. The energy stored on a capacitor depends on how much charge is on that capacitor and not how that charge got there. To understand the energy stored on the capacitor, we're going to think of the capacitor being charged by flow of charge inside the capacitor rather than around the circuit. At t equals 0, there's no charge on our capacitor. So when we move the first charge dq from the lower plate to the upper plate, it takes no work because there's no electric field inside our capacitor. To move the next dq will take some work because there's an electric field inside our capacitor, and we're pushing the dq against that electric field. The voltage across the capacitor is the amount of work to move 1 coulomb of charge from the lower plate to the upper plate. So the amount of work, dW, to move dq from the lower plate to the upper plate is the voltage across the capacitor times dq. So the voltage is the number of joules per coulomb, and the dq is the charge in coulombs, so the product of those is the amount of work in joules. For the voltage, we can substitute the charge on the capacitor over the value of the capacitance. As the charge on the capacitor increases, it takes more and more work to move each dq because the electric field inside the capacitor is getting larger. The energy stored on the capacitor is the total work it took to go from a charge of 0 to a charge of Q. So that total work is the integral from 0 to Q of dW, or the integral from 0 to Q of Q over C dq. C is a constant, so this is the integral from 0 to Q of Q of T dq, so that will be 1 over C times Q squared over 2 evaluated between 0 and Q. So the energy stored on the capacitor is Q squared over 2C. The energy is Q squared over 2C, but we know that the capacitance is the charge over the voltage. So we can substitute for Q, C times V. And so we get the energy stored on the capacitor is also 1/2 times the capacitance times the voltage squared. Now we're going to look at the energy density in an electric field. Let's look at a parallel plate capacitor of plate area S, plate separation D, and a voltage of V across it. We are going to ignore fringing fields. So the capacitance is the absolute permittivity times the area of the plates over the spacing between the plates. The potential across the capacitor is the electric field intensity between the plates times the plate spacing. In our equation for the energy stored on the capacitor, we're going to substitute this equation for the capacitance and this equation for the voltage. The energy stored on the capacitor is 1/2 the capacitance, which is the absolute permittivity times the plate area over the plate spacing, times the voltage squared, which is the electric field intensity inside the capacitor, times the plate spacing. This can be rewritten as 1/2 the absolute permittivity times the electric field intensity squared times the plate area times the plate spacing. The plate area times the plate spacing is just the volume of the capacitor. So this first term is the density of energy inside the capacitor. So the energy density in the electric field inside the capacitor is 1/2 times the absolute permittivity times the electric field intensity squared.